Hello, so I'm going to continue on the video on introduction to sets, and where we stopped was at looking at subsets. So the next thing of which that we would look at, for instance, is what we call a complement of a set. So let's say that we have a universal set U, and we'll just say that A is a subset of U. Now, what this means is that essentially we have an entire universal set in question, and we have that the set A will be like this. Okay, well, this is our set A, so we'll just put A right here. Now, what we want to look at is, in particular, everything outside of A. So everything outside of A has a particular name, and that's called the complement of A. So we have the complement of A. Now, the complement of A is essentially defined in the following manner. It's defined, and let's leave this here, it's defined as the set A such that X is an element of our set where X is in the universal set, and you have that X is not in A. So this tells us that X cannot be in our set A. Now, the complement requires that we always do know like what the universal set in discussion was. So if we had all registered voters and we want to find those that are not Democrats, then we would use the universal set of registered voters. Now, let's say, for example, that we look at a question where we have a universal set is given. So let's say that you have a universal set U equals to the set of elements 1, 2, 3, 4, 5, 6, 7, 8, 9, and we'll just do 10. Now, let's say that we have that A is equal to the elements 2, 3, 4, and 6. And then let's say that B is the set of elements, let's use 5, 8, and 9. Okay, so suppose that we want to find the complements of A, of B, and then last but not least, we'll just look at the complement of our complement of A. Okay, so these are very classic examples, and let's just put this here so that way we know what we're working with. So our set A complement, we have to use that that A complement is going to be the following. It will be everything that's not an A, so that's going to be 1. Well, 2 is already in there, so it can't be 2, 3, no. So 5, 7, and then 8, then 9, and then 10. So that's A complement. But if we look at B complement, let's do this. If we look at B complement, then what that's going to look like is 1, 2, 3, 4, 6, 7, and then finally probably just 10. So we have that will be that set for B complement. However, notice that if you're going to try to find A complement and you have the complement of the complement, well, it's everything that's not in A complement. So that would be 2, 3, 4, 6, and that would be it. So what that means is that the complement of the complement is actually its original set. So it's sort of like a double negative if you think about it like that. Now, the other operation that would be applied on types of sets or sets is what we call the intersection. Now, the intersection is actually very specific in the sense that, well, you have that your whole set in question is here. So let's say that we have two sets. We have A, and then we have B. Okay, but what if we were to shade the region between A and B? Okay, so we'll just call this A, and we'll call this B. So the intersection is basically where we have that the set is defined as A intersect B is equal to the set X such that X is in A, and let's just move this a little bit over, and we have that X is in B. So that tells us that we have the set A intersect B is all elements that are in both, essentially. Now, one thing to note is that we do have that sets can be empty. So like if we have that A intersect B is equal to the empty set, basically this just means that the sets are disjoint. Now, another term for that is mutually exclusive, which just basically means that they have nothing in common. So, for example, let's say that we look at a question where we have that the universal set is the values 1, 2, 3, 4, 5, and 6. Then let's say that A is the set of 2, 4, and 6. Then let's say that B is the set of elements 1, 2, 3, and then let's say that we have 5. Well, if we were to find, let's say that we want to find A intersect B, well, in that case, you're just looking for the elements of which are in both. So looking at A and B all together, you have that that's just the element 2. So we have that the elements that are in both of the two sets is just 2, and then that's it. So all that we had to do was just look at the two sets and decide like which ones have like, you know, the same matching members, which in this case was just the number 2. Now you can try to use a Venn diagram for instance, to do this, but this set was small, so we didn't really need to. And if you're wondering, like, perhaps, like, what does a disjoint set look like? If we go back and, we're thinking of, like, okay, well, what do you mean by disjoint sets? You can just look at the set like this, like you have A, and then you have B. So that would mean that you have two sets of which have nothing in common. Now, the last operation that we do look at on sets are the following. We have that we can look at the union. So we'll look at the union of two events. Okay, so the union, and we'll just start it off like this. So the union is basically a set X such that X is in A or X is in B. Now, typically, it's understood that it might be in both, which it's possible, but if not, then we just leave it alone. So, for instance, we have that the union of the two sets will look something like this, where we have a set A, and then we have a set B, and we have that this is going to be A, and this is going to be B. So our set union would have to be all the shaded portion and that would be it if we were going to try to visualize this. Now, of course, you do need to have that the universal set is denoted somewhere in here, so that way you know what's the set in question or what's the universal set in question. Now, when we look at, for example, the union of two sets, let's say that we have the following example. So in this example, let's say that we have a set 1, 3, and 5. And let's say that we have a set 3, 5, 7, and 9. So we just want to find the union of the two sets. Well, the easiest way to do this is in actuality to just say that, well, we remember that a union is really just the set of elements that are in A or B, or it's actually just the whole collection. So with that, we can actually say that the union of the two events A and B is given by 1, 2, 3, 4, 5. Yeah, 1, 2, 3, not 2. Okay, wait. I might have thought of another set. Okay, so yeah, just got to be careful with this. So we have 1, 3, 5, 7, and 9. And that would close out the whole set in actuality. So that would give us this set. So the answer is just collecting all of the elements and just writing them out in your set form. Now, for that matter, let's say, for example, that you wanted to use, let's say, for example, that you wanted to use the Venn diagram, Well, if you try to use the Venn diagram, let's move this over here and we'll just try to squeeze in this. So we have that that's going to be, okay, so we have, this is A, this is B. So we have that the elements that will be in the set for A will be, well, let's note this. There's a 3 in both of them, so that means that you have a 3 there. But then you have a 1, and then you have a 5. And then you have 5. Oh, wait. Actually, we have that that they both have a 5. So let's just delete this really carefully. So, okay, so yeah, I'm sorry, we're going to put a 3 there, and then we're going to put a 5 there. So it looks like there's only one element outside of the intersection, so okay, that's fine. So out here we have a 7 and we have a 9. But note that in this question, or in this example, there is no need to actually have, what is the universal set for this particular question. Okay, so the bottom line of this is that, if you're having trouble getting um, the um, the set and the collections, just draw a Venn diagram when in doubt.